Okay, good day, everyone. We already have three wonderful sessions on different topics related to visual learning, recognition, and reasoning. Thanks for Wenjun's invitation on organizing this panel. We can gather in here to discuss related topics in depth. We have four leading experts in this area for this panel. They are Professor Xilin Mu Lee from Seoul National University, Professor Ima from UC Berkeley, Dr. Katsu Ikeuchi from Microsoft Research Redmond, and Dr. Chong from Microsoft Research Asia. I'm Xilin Chen, and I'm from Institute of Computing Technology Chinese Academy of Sciences. I'm the moderator. Yeah. Yeah, here's the agenda. As mentioned in previous talk, deep learning plus huge training data becomes a popular, very popular paradigm in computer vision nowadays. After decades booming of deep learning, it's time to revisit the strengths and weakness of deep learning in computer vision. In this panel, we expected the panelists will give us some suggestions or recommendations on computer vision in next decades, both for academia and industry. We also would like to receive advices to next generation from these leading experts. After panelists sharing their valuable views on future of computer vision, we will have some debates on related topics. As all these discussions are very open, the panelists are expected to have a very short summary to the audience. Yeah, here's our four panelists. I will briefly just introduce them. Then they are invited to give us their position, views, and also about themselves. The four panelists are Professor Xilin Mu Lee from Seoul National University, Professor Ima from UC Berkeley, Dr. Katsu Ikeuchi from Microsoft Research Redmond, and Dr. Chong from Microsoft Research Redmond Asia. Not Redmond, sorry. I would like to invite them to share their position points within 3 to 5 minutes per panelist. Let's start from Professor Xilin Mu Lee. Xilin, please.
Okay, thanks, Xilin, for the wonderful introduction. I'm very happy to participate in this wonderful panel discussion with many good friends here. Actually, let me briefly introduce myself. I'm Kyoung Mu Lee from Seoul National University. I've been with Seoul National University since 2003, and actually I've been working on computer vision almost 30 years. Now I'm serving as a director of the interdisciplinary program in artificial intelligence in the graduate school of the Seoul National University, launched last year, which is the representative AI program in SNU, where now we have 53 faculty members who covers a broad range of AI, from core technologies to the many different application areas. So I have served the general co-chair of the ICCB 2019, and also served as the associate editor-in-chief of the IEEE PAMI until 2019. and will serve as the editor-in-chief of IEEE PAMI from next year. The research topics I've been mainly interested in are visual tracking, object recognition, low-level image and video restoration, and recently we are putting more efforts on the human pose and shape estimation, and also some fundamental, machine learning algorithms, especially for the application to computer vision problem like the meta learning, future learning, continual learning, and unsupervised learning. So, regarding the view on the future of computer vision, actually, we see that for the last decade, we observed that unexpected and unprecedented changes has been made in computer vision by the deep learning breakthroughs. Some specific problems that are considered hard to solve before, like object detection and classification, are almost solved, exceeding human performance, as you are all aware, right? I think that this trend will continue or be accelerated, even accelerated, at least for the next decade. Despite of these great advances so far, however, we are still far from the general human-level vision system for fully understanding the scenes. And many challenges, great challenges, still remain. For making real impact, developing robust and adaptive vision algorithms and systems that can handle extreme cases and really working, making really working system in the wild scenarios will be one of the most important issues. So in the roadmap to the artificial general intelligence or artificial super intelligence, I think the computer vision will still play a crucial and significant role. So we have a lot of chances to make it great difference in the future. Okay, so that's all. Thank you.
Yeah, thanks, Kim. Yeah, very clear points, and I think it's very helpful. He makes a lot of efforts on whitening the black box of deep learning. This is quite confusing for a lot of researchers. So I think his work is very important. And he just shared some progress on these topics. Yeah, he will give us incredible points. Please.
Thank you, Xilin, for introducing me, and also thanks for Wenjun organizing this panel, and also invite me for giving a keynote at this summit. As Xilin was alluded to, I'm Yima. I'm a professor at the University of California, Berkeley. My research interest has always been computer vision, as well as the mathematical principles or computational principles behind how to extract information from high-dimensional data, such as images. And as Xilin mentioned, that also Kyoung Mu in his presentation mentioned that deep learning has tremendously changed, advanced the practice of computer vision. But for a while, the deep network has always been used as a black box, right? Despite the empirical success, the understanding of what really the deep learning is doing, as well as what the role of deep networks, has always been challenging. So some of my recent work has really trying to open that black box up and provide a purely white box approach to derive deep networks from the fundamental principles of information processing or data compression. So I gave a talk about that at this summit. More related to this panel, right? And my work in how do we provide such a lookout for the future of computer vision. So the specific area I worked on computer vision is more related to 3D vision, and we all see that the classical 3D vision has always been trying to recover 3D model from a sequence of images, right? By establishing correspondence and recover the camera position and also the 3D location of the feature points. This is sort of the basis for the classical 3D reconstruction pipeline. We have seen a lot of practical success, including the SLAMs and so on, simultaneous localization and mapping, relies on this kind of technology. Of course, this also has this kind of classical approach has troubles, right? And we know that when the scene has lack of texture, different type of reflection or repetitive patterns, large baseline, right? It has always presenting challenges to this kind of classical approaches, which also suggest to resolve 3D reconstruction, we also cannot just exclusively rely on geometry. We have to rely on recognition. So hence, in the past 10 years, right, deep learning also has really tremendously improved the capability of computer vision in tasks such as recognition. However, on 3D reconstruction, this deep learning has met some challenges, right? Despite the tremendous progress, we're able to infer 3D pose, voxel, point clouds, or geometry or depth, or even surface. And a more serious evaluation of these methods actually suggests that the deep networks, at least for the task of 3D vision, is actually not that necessarily better than very primitive methods such as nearest neighbor. So now the question is, how can we combine the classical geometry-based techniques with the high-level recognition, data-driven recognition that boosted by deep learning technology? I think that would be the challenge for the future of 3D vision, right? So really that how be able to combine the principles of geometry as well as the data-driven learning technology, right? Enhance the ability in recognition. So there has been some recent work we were trying to combine this classical geometry with the learning-based method, right? Truly that be able to use recognition techniques, learning-based techniques, to learn and detect and correspond high-level features, lines, planes, and vanishing points, symmetry, and so on and so forth. I think this sort of marked a good paradigm to combining geometry with learning-based method, and this is what I think would provide a very many exciting problems for future of computer vision. Yeah, thanks.
Yeah, thanks, Ima, for his wonderful, I think, points. And as Ima, even he didn't mention that, Ima didn't mention that his book, many years ago, he wrote a book on 3D vision. And the 3D has a very beautiful mathematics like geometry and others. And nowadays, data-driven should be combining with this beautiful mathematics. Thanks. Okay. Katsu keeps working in this area for more than 40 years. And his experience and prospects definitely will be very helpful to the young generation, because he started from that age, shift from shading, optic flow, and very traditional and typical topics in this area. Let's invite Katsu to share his wisdom. Katsu, please.
Okay. So basically, long time ago, I got a PhD at U Tokyo and then worked at MIT, ETL, CMU, and U Tokyo, and then Microsoft. And then, I have worked in 3 areas: computer vision, robotics, and ITS. And in computer vision area, basically, I mainly work in physics-based vision, and then robotics so-called learning from observations. And also, altogether, I work combine everything into the e-heritage to preserve cultural heritage by using computer vision technique and robotics technique. So that's my introduction. And now I have couple of the future view. But in order to know the future, we need the past. So-called onko chishin in Japanese and Chinese and whatever. First of all, from where we come from. And in my opinion, or everyone knows that AI began at the Dartmouth Conference, 1956. Four or five great people, including McCarthy and Minsky and other people. And at that time, computer vision robotics are synonym with AI around that time. In fact, around that time, Artificial Intelligence Laboratory, MIT, one of the center of AI research at that time, completed the following demo. One is MIT AI copy demo, sensing the block world, and then understand the structure of the block world, and then create a structure by, at that time, 3 PhD students. Now they are great computer vision professor at MIT and Stanford. And then some of them passed away actually. And then 10 years later, I and BKP Horn developed a beam picking demo. Now again, BKP Horn, Marvin Minsky, and Pat Winston think that is one of the direction which we should go. And at that time, we sense so-called donuts by using photometric stereo and determine surface orientations. And then, based on this surface orientation, we determine object attitude by using Gaussian, extended Gaussian image and grasp plan. So important point is previous system and current system. Previous system and current system that consists 3 components: sensing, cognition, and action. And the purpose of the Artificial Intelligence Laboratory was to create artificial life form, which consists of these 3 components. However, Marvin Minsky and other people realized each of the 3 components poses challenges, and then reductionism occurs. Let's divide and conquer. Since sensing developed a computer vision in 1987, from Ichikai, ICCB was separated. And then 1984, from Ichikai, robotics conference called ICRA was separated. And since then, computer vision and artificial intelligence and robotics are researched in parallel manner. And then, half century later, Cambrian explosion occurs in robotics as well as computer vision. And of course, the reason why Cambrian explosion occurs is, in biology, acquisition of vision was the main reason why Cambrian explosion occurs. Then why computer vision a Cambrian explosion occurs? Well, computer vision, acquisition of deep learning and cloud technique is the main reason why such Cambrian explosion. Cambrian explosion is a good idea to make many different techniques. However, the result of Cambrian explosion is extinction. Too many species, so most species were extinct. Only those optimized to environment can survive such vast extinction. So it means computer vision, there is a possibility such extinction occurs. Then what we should do? We need a paradigm shift. Previously, we are mainly talking about reductionism to make discipline fragmented and divide and conquer. But discipline is too fragmented, and due to that, in one sense, explosion occurs. Now we have to come back to the origin. to move to holism, and that holism system to adapt the environment so that we can survive, or our community survive. We need a paradigm shift from reductionism to holism. And the important point is, in this holism, we have to worry about environment. Previous AI system, artificial life form, we didn't consider environment. Then what is the environment? Well, first of all, why we are making artificial life form? Our artificial life form should work for human in the human environment. So for the computer vision, artificial intelligence, and the robotics, artificial life form should worry about environment, human societies. So we have to make the artificial life form for human societies. And currently, we can think about two types of artificial life form. One is Terminator type, enemy type, to compete human, and complete autonomous system. Another one, in Japanese cartoon, there is a cartoon called Doraemon. This is a friend of human and cooperate and help human and augment human physical and intellectual abilities. We should aim this Doraemon type artificial life form. One more thing, does any of the module current deep learning want to learn? I don't think so. Does any module have self-consciousness? I don't think so. If the goal to build the artificial life form, we should aim to design artificial life form with self-consciousness to help human. And in fact, by thinking about this one, recently we are working artificial life form to serve seniors. Most of the seniors in assisted living facility would have preferred to remain at home. But if we can make a robot which learns what to do from demonstration, then caregiver can teach artificial life form at home, and then such artificial life form can help seniors to enjoy their living at home and empower them to be able to achieve more. So in my opinion, of course, this is just one example, but we should worry about this kind of artificial life form. Thank you very much.
Thank you. Yeah, Katsu. Yeah, it's very, I think it's very important points for future researchers. Yeah, because vision is just a part of function of artificial intelligence. And even for the whole AI should be also working with the body. So embodiment AI with even computer vision should be the future in the maybe next 10 years. Okay, next, let's move to our last panelist, Dr. Chong Lo.
Hello. Hello, this is Chong Lo from Microsoft Research Asia. I'm currently a principal researcher with the Intelligent Multimedia Group. I'm also an adjunct professor and PhD advisor in the University of Science and Technology of China and in Xi'an Jiaotong University. Yeah, in the past, I actually I'm not in the computer vision field for all of my research career. Actually, I start my research career from computer vision, but then in the middle, I worked on video communication, joint source coding of video, and then coming back to computer vision a few years ago. So currently, I work on image and video understanding, including image classification, object detection, and visual tracking. And also, one of my main interests recently is to do disentangled visual representation learning. And I also work on multimedia editing, including both audio and video processing and generation. So in talking about the future of computer vision, so I think the computer vision research, just as other the research in other domains, can have blue sky research or mission focused research. So I think both type of research are important because blue sky research help us to push the frontier of the research and of the human ability. And mission-focused research is really practical research that is useful, right? So I think in blue sky research, I'm quite interested in representation learning and especially the disentangled representation learning, and also the cross-modality learning. So vision actually is one of the human senses. So I believe computer vision should only be one of the computer senses. And all the senses, for humans, all the senses work together to sense the world. So I think for computers, it is also our ultimate goal to let different computer senses to work together. So I believe the cross-modality, including vision, language, audio, and other kinds of sensors, all these things should work together. So in one short word, computer vision is not alone, and we should think of other senses. And also this is, I think, consistent with Dr. Katsu's view that we should think computer vision in an environment. And as for the mission-focused research, I think we already see many applications of CV in the manufacturing industry or in some retail industry. For example, the face recognition, some scratches recognition. But for me, actually, my focus is on improving the efficiency of information workers. So this might be related to Microsoft vision because the vision of Microsoft is to empower every person and every organization on the planet to achieve more. So the mission of our group, the Intelligent Multimedia Group, is to build seamless yet efficient multimedia applications and services through breakthroughs in fundamental theory and innovations in algorithm and system technology. So I'm particularly interested in improving people's efficiency, especially information workers' efficiency through the advanced computer vision technologies. So I think I will stop here. Thank you.
Okay, thank you, Chong. Yeah, it's. I think all the panelists share very valuable points, and all these points are very important for us. Yeah, we also prepare several questions for further discussion. Okay, and as you know, deep learning has been a dominant tool in computer vision for almost 10 years. Yeah, maybe from 2012. Yeah, and it seems to get very successful in task-driven applications, like just Chong mentioned. Very successful in specific area like object categorization, autonomous driving, face recognition, and etc. From these cases, computer vision seems to be a application of deep learning or machine learning now. Yeah, many researchers said, it's just an application of machine learning. But as we are, most of us, we start our research from computer vision. And at that time, computer vision was a very beautiful area with physics, geometry, psychology, and other very interesting topics. It seems all these modules are behind data at this time. So I would like to ask your question about what's the unique aspects of the computer vision in nowadays. Okay, maybe, okay, because this is a free discussion, okay, just give your opinions. Maybe, Ima, could you give us first your ideas? What's the,
Thanks for, this is a very good question. I believe actually probably Katsu in his presentation already alluded to a good answer to this question, right? Computer vision actually has very originated from very diverse the domain knowledge, physics, photogrammetry, robotics, and so on. Right. From my personal point of view, so the learning-based method, data-driven method, has been very successful in terms of very task-specific setting, where maybe the model of the problem, physical model or geometrical model of the problem, is not is difficult to derive. So in the area that I showed in my slides, right, when you have the task is very demanding in terms of accuracy or in terms of performance guarantee, then the domain knowledge, such as geometry, become extremely important. The purely data-driven method so far has failed to be able to produce the kind of method, the results meet the kind of accuracy, such as in 3D vision, right? You get very, very good results, but they are, in terms of accuracy and in terms of robustness, they're actually quite lower than what the geometric method can give you. But they're very, very complementary to what the geometry. That's actually something that I think is important. On the other hand, even from a learning point of view, even, let's say, geometry can be learned autonomously from the data. It may not be even necessary, right? Every single time you build an autonomous driving system, that system has to be trained to learn all the fundamental geometry we already know, right? Hence, I think there's a great success, better success in the future for the deep learning or for computer vision is precisely to combine the power of data-driven method with the domain knowledge that the computer vision has developed in the past on geometry, on the photogrammetry, on the physics, on the kinematics of the robots, and so on. Right? Hope that answers your question.
Yeah, actually, why computer vision is unique? Because DNN itself is invented from the human visual system, and computer vision try to make an alternative of human visual system. So they are perfect match. And so basically, human visual system try to make a continuous low-level signal into symbolic representation, and the DNN is a suitable mechanism. So both computer vision and deep learning area cooperate each other, and future is bright. Actually, that's my opinion.
any opinions from Chong?
Thank you, Prof. Chen. This is a very good question. Yeah, I think if you just use deep learning as a tool, then I think not only the vision domain, actually deep learning can be a tool actually to many other domains. And we cannot say that all the domains are just applications of deep learning, right? Because each domain will have its own uniqueness. And I think at early stage, when deep learning shows its power, people just apply deep learning to various areas and achieved many good results. But eventually, I think the domain knowledge will play an important role. Just as Prof. Ma just mentioned, I think not only the geometry, but also the knowledge about the appearance, about the other appearance knowledge, I think will play some role in for us to better understand from the vision system. Yeah.
Okay, thank you. Yeah, another question related to the first one is, in recent days, benefiting from the very rapid progress of computational power and huge data, network becomes deeper and deeper. Even maybe thousands layers. Is this the right way to solve the computer vision problem? Because some researchers just believe that we have more data, we have more complex network. All the problems seems could be solved. If it's not, what's the right way? I know, you just mentioned maybe some other, ways, but, some people, just believe this probably can even to solve the general purpose computer vision. I think it's quite close to the last question. So you can, very briefly give your ideas.
Yes. Okay. So yes, you all are aware of recently big companies are investing a lot of huge resources to build hyperscale AI systems, right? Like the GPT-3, something like that. So it requires a huge amount of computational power and also a huge amount of data. So I think it's a good try. So because we haven't explored how far we can reach in terms of accuracy or performance of CV algorithms with the scalability of the network capacity or the computational power and data, as I mentioned. So you remember that the resurgence of deep learning, around the 2010, is mainly due to those factors, right? Computational power and large data and new, network capacity, something like that. So we'd like to see how we can, go further. As though how to make those big networks applicable or deployable to real problems. So will be an interesting and challenging problem still. So in that respect, actually, the academia can play a big role competing with the big companies, right? Yes.
Any others? Or we just move to next one? Okay, let's move to the next one. Okay, so as a part of AI, computer vision is closely integrated in interaction with NLP, robotics, and other related fields in recent years, just like Katsu mentioned in his points. Meanwhile, multimodal sensors are also integrated in a vision system. It's far beyond our human vision system because it can integrate other modalities as sensor. And this does bring a lot of new topics in this community. From your experience, what is the new challenges? I mean, because a lot of people working just on large models or explainabilities and others. What's the most important topics in the next few years? Yeah, this is quite close to Katsu's points.
Yeah, actually, as Ima said, we don't need to train DNN from scratch. The issue is, how to fine-tune previously pre-trained network using small data as humans do is the first challenge. And second challenge is science only progress only when the contents are understood by us. So self-explainability of the process is again challenge of DNN. And third thing, as I mentioned in my previous talk, does any DL module want to learn, or does any DL module have self-consciousness? Probably no. And is it possible to make such a self-aware or self-motivated DNN to improve or to adapt the environment? That is a big challenge. Thank you.
I can add to that. Honestly, I think there are grander goals, but I think if I wanted to challenge the learning community and the vision community together, right? We need to understand the computational mechanisms of how our visual inputs become our memory, right? And also compute it against it, right? For example, we can train very large data network, but it's very hard to extend it, right? And if there's additional class, we all know our memory. We can incorporate, enrich our memory by incorporating new classes, new objects, new experiences, without interfering with the things we have learned in the past. And the current practice of deep network, that has been a very big challenge for that. How do we build, establish memory, learn from our past visual experiences, and also be able to add upon to that memory, and then use for future decision making or for our perception and so on. And I think that's a more tangible task that pose a challenge for the current practice of learning or computer vision as well.
Yeah, as Kimo just mentioned, they're short learning or they're short computer vision. So I think this is also related to the extendability. Kimo, what's your opinion?
Yes, actually, current DL deep learning systems, especially for the computer vision, most of them are passive and static, right? So usually we human collect the data set and then train the system. Then the system usually give the answers conditioned on the provided data, right? So generalizability is an issue. So we actually experienced, many times that the system performance on the benchmarks is quite impressive. But when you try to apply those systems to real problem in the wild, then the gap is quite large. So that's a big, issue here. So I think that we have to solve this issue to make the system, deep learning system, to be, active and dynamic, right? So that the system itself can improve by itself and solve the problem. So this is quite related to the data issue. So the unsupervised learning or unpaired learning or self-supervised learning could be the highly important issue. So how to construct the real data, and or how can it generate realistic data set? How can it come up with the future, situation, how to make the system progressive, something like that. So those are quite, essential issue we have to tackle in the future.
Chong, do you have any idea?
Yeah, a very short answer. I think the biggest challenge is how to combine knowledge, memory, and data to make the computer system more intelligent.
Okay, thanks. Yeah, as Katsu mentioned, that vision should be a part of AI and should be working in a system and within an environment. So computer vision at beginning, we try to make a general purpose system or general purpose functions. But in the last 20 or 10 years, we get quite success in task-specific vision system. So is that time for us to go back to general purpose vision in research community? Because we cannot. I think we cannot. Just use deep learning to solve problem by problem. We need a general purpose system. If the answer is yes, then what's the possible roadmap towards this goal?
Let's see. Apparently, this general vision argument is coming from human visual system. And certainly, human visual system looks like a general purpose vision machine. But I consider it as a collection of special purpose vision machine. For example, when you run a new vision problem, originally you try to solve it using all your consciousness. However, for example, driving. However, when you get used to it, you can handle the same problem while working on other problem. So apparently, some of the modules become special purpose vision machine. So along this line of thought, we can consider what kind of task division will cover the entire domain in artificial life form environment with optimum divisions, and create what is the optimum collection of special purpose vision machine to corresponding to those divisions. So that's kind of issue which we should try to solve. Thank you.
Okay, thank you very much for your very constructive points. And as we have only very limited time, so I have to move to the last parts. Could you give one very short summarize on your points? Let's start from Chong.
Okay, so I want to say that computer vision is not alone, and data is not everything. We should combine computer vision. We should consider computer vision in a more comprehensive sensing system. And we also, when we tackle the computer vision problems, we should also consider knowledge in addition to data. Thank you.
Okay, thank you. Then, Katsu.
I would like to share my screen actually. So basically, we have to build a friendly artificial life form, and artificial life form should be friend of human, and human is a master and creator of the system. And artificial life form should not aim 100% autonomous intelligence, but should aim at 90% of augmented intelligence. The reason is, I'm talking about a paradigm shift from reductionism to holism. But we shoot at 90% of holism. But this cycle is just one cycle, and repeating this infinite loop of reductionism, holism, then we can create artificial life form for understanding ourselves and for understanding better human environment by combining three major areas: computer vision, robotics, and AI. 100 times, 1,000 times, 3,000 times. Thank you very much.
Thank you. Yeah, can you give your summarize?
Yes, I always has the view, right? The nature operates in the most simplistic and fundamental way, rules and principles, right? In terms of safe space, energy, resource, right? And also I believe there is a chance now we could, through some of those principles, to understand, right, the computational process or mechanism that behind how those mechanisms makes our human visual system so efficient, so effective, and so diverse, right? I think we are sort of at that verge to really be able to discover some of the computational principles now. And thanks for some of the advance in deep learning or understanding of machine learning or data analysis. Yeah, that's my view. Yeah, but hopefully in the next 10 years, we'll be able to discover those mechanisms. Simple, but universal and effective rules.
And important, yeah, it also works. Yeah. Kim, it's your turn.
Okay. I believe that the computer vision is not over, but it just has started a new era. Okay. We have lots of new, interesting, and challenging vision problems ahead of us. The solution of them will play a vital role and eventually will lead toward the human level AI. So let's enjoy the journey together. Thank you.
Okay, thank you all the panelists again for their very thoughtful sharing. Computer vision is a very important topic and still has a lot of valuable problems to be solved in the future. And thanks for all the panelists and the audience. Thank you.